Okay, so this mini lecture is going to look at using forces to solve problems and how we do a force analysis. And what are some of the steps and procedures that we can use to be very comfortable and confident moving forward to very complicated problems. So really looking at what is the force analysis process. We're going to use a very simple example for that, and we're going to develop the force analysis process through this example. So the example says you're getting ready for a birthday party and sliding a bookcase, which has a mass of 100 kilograms, across the floor. The coefficient of kinetic friction is 0.5, and the coefficient of static friction is 0.63. What is the force necessary to accelerate the bookcase at a rate of 2 meters per second squared across your carpet? So what force as the bookcase is moving is necessary to accelerate it? Now you could probably immediately put in a problem, and that is fine, or immediately find an answer, but I want you to use this problem, we're going to use this problem to very systematically define how we're going to solve problems with using forces and doing a force analysis. So the first step in our force analysis problem solving, I'm just going to the first step is to identify the object. So in our example here, our object is the bookcase. The bookcase is what we're moving across the floor. So we're going to be explicit about that. And we've been doing this. We've been identifying the object and the interactions. All right. So the second part of the process is going to be to draw a picture. And as we move to using force analysis to do analysis of motion, that picture is going to need to have a coordinate system and an origin. So of importance with a force analysis is definitely the coordinate system. We're going to find that a lot of times we might want to do an analysis that gives us an altered coordinate system, a rotated coordinate system, to make solving the problem easier. So drawing that picture to be able to identify that coordinate system is going to be important. Now, how do we identify the coordinate system? What do we use? Well, let's draw a picture of our situation here and use that to help give us a sense. So here's our bookcase, and I'm pushing it along the floor. So it's moving, it's accelerating in the rightward direction in the example that I've given. Typically, you will want to align the coordinate system with an acceleration. You want to align the coordinate system with the acceleration. So if the acceleration is along the horizontal axis, I will want a coordinate system that is aligned with that horizontal axis. And we'll use that coordinate system then on our free body diagram. If, for example, I was moving that bookcase up a ramp and accelerating it up a ramp, then I would want to align my coordinate system along the ramp. It'll make problem solving a lot easier in our analysis. All right. If I'm going to be doing kinematics, if I want to identify how far this bookcase goes after 3 seconds, so a kinematics process, and we'll do some examples of that, then in addition to my coordinate system, I have to identify the origin. So it's not a bad habit just to get into the habit of doing that on our picture so that we're prepared when we do have to analyze motion of an object. All right, so on that picture, we align with the acceleration, so sometimes it's going to help us to identify the direction of that acceleration. We might want to do that on our free body diagram if we can be very careful not to include it as a force. But at least on the picture, we want to identify that direction of acceleration so we can identify that coordinate system. Okay, so I've identified the object, I've drawn my picture, it's time to identify the interactions. And I'm going to put this as a separate step from the free body diagram. But as we've been practicing, you can do these 2 steps concurrently. So if it helps to draw the free body diagram as you're identifying forces, perfect, do that. All right, so for my interactions, it's the object that I'm interested in. And so what is the object interacting with? Well, we know that there's going to be the force of gravity. So that's between the bookcase and the earth. And we know that acts in the downward direction. So here's my force of gravity, equals mass times gravity. All right, other interactions. Well, the bookcase is on the ground, so I know that there's a contact force, a normal force, between the bookcase and the ground, and that's pointing in the upward direction. So there is my normal force. Now it says that I'm pushing the bookcase along the floor, so there's a force of a push. And that's between the bookcase and the pusher. And in this example, we're saying that that is to the right. So here's our force of the push. The question also suggests that friction is present. Now, friction is always in the direction opposite the motion or the intended motion. And so in this example, the friction, if the object is accelerating and moving to the right, then the friction must be to the left. What type of friction is it? If I've gotten the object to move, then this must be kinetic friction between the bookcase and the ground. And it's to the left. Now remember, and I did it both ways, if I draw my arrow on my free body diagram first, and I can't identify two objects, no force exists. Or if I identify an interaction but I'm not able to actually get that second object, no force should go on that free body diagram. All right, so I think these are all the interactions. All right, so we have 4 interactions, 4 forces are going to be represented on my free body diagram. All right, next step is to separate the forces into horizontal and vertical components. This is important. This is a remembrance that it's the net force that causes changes in motion. It's the net force that's important. It's the net force that influences the object. And so in order for us to understand the net force, we have to understand the forces separated so that we can look at the forces in the horizontal separate from the forces in the vertical direction. All right, I like to number my forces so that I can make my list clear. So it doesn't matter the order, but this is a decent order. So the force of the push will be force number 1, the normal force number 2, kinetic friction 3, and the force of gravity number 4. So we're going to separate our forces into horizontal and vertical components. So force number 1. So now we want to look. Does it have a horizontal component? Yes, it's to the right. Does it have a vertical component? Nope. So my horizontal component is a positive force of the push. Do I know what that force is? Nope, it's not given in the problem. So we're just going to leave it as a positive force of the push to the right. Okay, force number 2. It's normal. Does it have a horizontal component? Nope, it's only pointing upward. So it has a positive, not given its magnitude, but the horizontal component is, the horizontal component is 0. It's only pointing in the upward direction. Force number 3. Well, that's pointing to the left. No vertical component, and it's pointing to the left. So I have to remember that I have to put that negative in. So my sign is relative to how those arrows are pointing. So negative frictional force, and it's useful to help us remember that that's minus the coefficient times the normal force. So that's an equation. It's not given, the coefficient's given, but the actual value of that frictional force is not given in this example. But we do know that it's related to the coefficient times the normal force. And finally, force number 4 does not have a horizontal component, only a vertical component. It's pointing in the downward direction, and we want to keep in mind that's minus mg. So here are our 4 forces separated into horizontal and vertical forces. All right, so the next thing that we do is apply Newton's second law. This is the one that says the net force is equal to the mass times the acceleration. Keeping in mind that means the horizontal net force is equal to the mass times the horizontal acceleration, and the sum of the vertical forces is equal to the mass times the vertical acceleration. So this is that separated Newton's second law, so separating the two forces and then looking at how there is a net force in the horizontal and the vertical direction. So we're going to sum the horizontal forces and we're going to decide, is there indeed an acceleration? So this is mass times acceleration horizontally, and this will be the sum of the forces vertically, mass times acceleration vertically. Now given this problem, is there an acceleration horizontally? Yeah. The bookcase is moving along the carpet in the horizontal direction and it's accelerating. What about vertically? Well, it's not changing its motion up or down. So there's no acceleration in the vertical direction in this example. All right? So that's important application of Newton's second law. Okay. After we identify which direction the acceleration is in, we continue to apply Newton's second law and sum the forces. So the sum of the forces horizontally is equal to the force of the push minus the frictional force, u sub k, times the normal force. That equals mass times acceleration horizontally. Vertically, the sum of the forces is equal to the normal force minus mg. That is equal to 0. So we've summed our forces and applied Newton's second law, which is the application of Newton's second law. The next step is simply to solve for what we're interested in. Now, we are interested in what force is necessary. What is the force of the push? So we're going to solve for the force of the push. The force of the push, if I add mu sub k n to the other side, I get m times the acceleration horizontally plus mu sub k times n. Well, I know m, I know a, I know mu k, but I don't know n. Well, I look for n in another relationship. Is n related to anything else? Yeah, the vertical. If I solve for n, I get n is equal to mass times gravity. So in this case, my mass was 100 kilograms. So 100 times 9.8 is 980 newtons. So n is equal to 980 newtons. Now I'm just going to shift this equation over because I'm afraid I won't be able to show the relationship. So I'm just going to put it over here. I'm going to give it a little border. So I have F of the push, which is what I'm solving for, is equal to the mass, 100, times the acceleration we said was 2, plus mu sub k, ooh, I've forgotten what we said that was already, 0.5, times the normal force of 980. And once I have that relationship, I can solve for the force of the push. So 200 plus half of 980 is 490. I get 600, could have done that in my head. I get 690 newtons is the force required to push that bookcase at 2 meters per second squared. All right, so what was the process? That's what's important in this particular example. We had to identify the object that we were interested in. Once we identified that object, we needed to identify a coordinate system. So we drew a picture, and we looked at what direction the acceleration was in. We aligned that coordinate system with the direction of the acceleration. And as we move to angles, that's going to become a little bit more clear, because right now it's just in our regular coordinate system. We often will use forces to analyze motion, and therefore we also might want to consider putting an origin on just to get in the habit. We then draw a free body diagram and identify the interactions. Those can be done simultaneously. And making sure that every force that's acting on this object we've identified the interactions for, and that we've identified the arrows and represented them on a free body diagram. Then we can go after the meat of the problem. Separate the forces into horizontal and vertical because we can't do anything with them if they stay in vector form. Apply Newton's second law, so sum the forces and apply Newton's second law to that sum. That's what Newton's second law is about. Recognizing which of the two dimensions that we've identified the direction of the acceleration is in. And then we simply solve for what we're interested in. And oftentimes we're going to have to use multiple equations to get to that solution, recognizing that these ideas are related and that the normal force that's acting on the object is the normal force that friction is dependent on as well. So using that conceptual understanding to recognize where I can get to information if I don't know it. All right, practice these. There's some example videos, and then of course your homework and your discussion activities. So let's get this understood. All right, good job.